Section 8.6, limiting reactants, theoretical yield, actual yield, percent yield. In industrial applications, the concepts of theoretical yield and actual yield are very important. And you can adjust the amount of reactants, so you basically get to choose what's the limiting reactant. So in an industrial situation, they will generally choose the more expensive reactant to be the limiting reactant, so that you make sure you use up all of the expensive thing and you've got cheap stuff left over. Or they will choose the reactant that's hardest to remove from the product so that you don't have to deal with it later. When we're working in the lab, obviously we're measuring things in grams and not in moles. And so we need to learn how to figure out these yields in terms of grams. So this is just adding a step on the beginning and a step on the end. So we're going to talk about this reaction. Just kind of look at the pictures, and then we'll actually do some examples. So here we have sodium and chlorine reacting to form sodium chloride. It's just so much easier to look at it over here. So we're given 53.2 grams of sodium and 65.8 grams of chlorine, and they're asking us to find the limiting reactant and the theoretical yield. So all the words around this are gone, and this is just distilled down to the important information. So we look at this and we see that we are given two reactants masses, and so that's going to tell us this is a limiting reactant problem. So what we're going to do is we're going to have two different calculations, but now instead of going from moles to moles, we have to do that full-blown thing. Grams to moles to moles to grams. Grams to moles to moles to grams. Grams to moles to moles to grams. So we start with one reactant here, the sodium. We go grams of sodium, moles of sodium chloride, grams of sodium chloride. The other one is the chlorine, and we follow a very similar path, ending up at the same place. The conversion factors needed here in the middle one, the mole to mole, these are numbers from the balanced chemical equation. So 2 moles of sodium chloride are formed from 1 mole of chlorine. So those are the easy ones. These aren't that hard. This is molar mass of sodium, molar mass of chlorine, and then you get a little bit of like a bulk discount here for doing 2 equations. The last term is the same because you're going from moles of sodium chloride to grams of sodium chloride, so you get to use that molar mass you have to calculate twice. So we calculate these, and then we're finding the smallest amount. So here they are all written out. We see that from the sodium we could make 135 grams of salt, and from using up all the chlorine we could make 108 grams. So the theoretical yield is the smaller amount, because like when you're making pancakes, when you run out of an ingredient, you have to stop making pancakes. In a chemical reaction, when you run out of a reactant, it stops, no more. So it's the smaller amount. That's the theoretical yield, and the reactant that produced that is your limiting reactant. There's a piece missing in this question here. It says find the percent yield, but they don't give you the actual yield. They would need to tell you that the actual yield is, what is it, 86.4. So if they tell you the actual yield is 86.4 grams, they can ask you what's the percent yield. The percent yield is the actual yield divided by the theoretical yield. We just calculated the theoretical yield. So we put those numbers into the equation. Here's the actual yield divided by the theoretical yield times 100%, and we end up with a yield of 80%. Any questions so far? So let's do an example. Ammonia can be synthesized by this reaction. 3 hydrogen molecules plus 1 nitrogen molecule yields 2 ammonia molecules. What maximum amount of ammonia in grams can be synthesized from 25.2 grams of nitrogen and 8.42 grams of hydrogen? So let's take that balanced chemical equation. You would need to write that down on whatever paper you're doing your work on. And then we take those masses and we write them under the appropriate compounds. So 25.2 grams of sodium and 8.42 grams of hydrogen. The question is, how many grams of ammonia? Maximum amount in grams. We're given 2 reactant masses, so it's going to be a limiting reactant problem. So that means we do 2 equations, grams to moles to grams. So let's just start with the hydrogen because that one's first. 8.42 grams of hydrogen. 3 factors here. Grams of hydrogen to moles of hydrogen, to moles of ammonia, to grams of ammonia. So even if you don't try to remember that, you may do it in spite of yourself just because we use it so much. Grams to moles to grams. Then we fill in the units so that they cancel out. Grams of hydrogen down here because we want to cancel that one. Moles of hydrogen down here to cancel that one. Moles of ammonia down here to cancel this one. It's all about the units. Anybody have any questions about why those units go there? The middle term is the easiest to figure out. Mole ratio. It's a mole to mole. So you look at the balanced chemical equation. In front of hydrogen is the number 3. So we put 3 in front of hydrogen. So remember, what we're really doing here is we're thinking, well, it's 3 moles of hydrogen reacting to form 2 moles of ammonia. And it's 1 mole of nitrogen. That's what the balanced chemical equation means. And in front of nitrogen, ammonia, we have the number 2. Then we need the molar masses for hydrogen and for ammonia. In these, we take the formula H2. There's 2 hydrogen atoms in 1 molecule. There's 2 moles of hydrogen in 1 mole of hydrogen gas. And so that's going to be 2.016. This is 1.008 times 2. I'm going to do the other one up here on the top. Nitrogen is 14.01 and 3 hydrogens. And that comes out to be 17.034. I'm a little afraid that I remember that, but that is not a 2. That's a 7. That's better. Grams of ammonia equals 1 mole of ammonia. That's the molar mass of ammonia. So that's what goes in this last term. The number goes with the grams. And that's per 1 mole. Now, I did this problem yesterday, but I don't remember the answer. That would be truly frightening. And a waste of brain memory space. 8.42 divided by 2.016 times 2 divided by 3 times 17.034 equals. Then your calculator gives you a whole bunch of numbers. Yield is our final answer, so let's round this off. We started with 3 significant figures, so we're going to express our answer with 3 significant figures, and we get 47.4 grams of ammonia. Anybody else get that number? Okay. So that's that's one possibility. But then we have to take the other reactant and find out how much product it could make. So 25.2 grams of nitrogen. Same pattern here. 3 conversion factors. Grams to moles to moles to grams. Grams of nitrogen to moles of nitrogen. 2 moles of ammonia, 2 grams of ammonia. Divide by the previous unit, because we want all those other units to cancel out. And yeah, it seems like kind of a long process, but there's really no shorter good way to do this. So we need the molar mass of nitrogen. Nitrogen is one of those diatomic elements. So it's 2 times 14.01, or 28.02 grams of N2 equals 1 mole of N2. So 28.02. The number in front of nitrogen in the equation is an implied 1, and the number in front of ammonia is still a 2, and the molar mass of ammonia hasn't changed, so we can just copy that one down. We don't have to calculate it again. That's your little bonus there. Like, woohoo. 25.2. You got to be thankful for the little things. Times 2, 17.034. Okay, so we're going to round this to 3 significant figures also. So what we figured out is that if we were able to use up all the hydrogen, we could make 47.4 grams of ammonia. If we were able to use up all the nitrogen, we could make 31.2 grams of ammonia. The smaller number is the most ammonia we can make. Because we're making ammonia, we get to 30 grams, 31 grams, 31.2 grams, and we run out of nitrogen. You can't make any more. If you had more nitrogen, you could make more, but you do not have more nitrogen. Okay, sometimes students are like, yeah, but 47's bigger. Well, yeah, 47's bigger, but you still can't do it. There's our answer for the maximum amount. Any questions? What's the limiting reactant in this problem? It's the nitrogen, because the nitrogen got used up. Here's another one. This reaction is used to obtain iron from iron ore. I'm sure you're just excited to learn that today. The reaction of 185 grams of Fe2O3 with 95.3 grams of CO produces 87.4 grams of Fe. Find the limiting reactant, theoretical yield, and percent yield. You're like, there's 3 numbers. They're asking for 3 different things. Don't panic, okay? Hitchhiker's Guide to the Galaxy. Don't panic. Written in big friendly letters on the cover. It's just good advice for life.
42.
And the answer is 42. Now, if the answer ends up being 42 like it did the other day, then I'll be scared. Okay, so let's take these numbers and write them under our equation, just to kind of help get rid of those words. So 185 grams of Fe2O3. So 185 grams of that. And 93.2, 95.3 grams of carbon monoxide. And it says that makes 87.4 grams of iron. Like, okay, this is different. They're giving us the massive product. What's up with that? Well, now let's turn and see, what are they asking for? They're asking for the limiting reactant and the theoretical yield and the percent yield. And so, you know, a student may say, well, isn't 87.4 the yield? Well, it is a yield. Is it the theoretical yield? No, that's the actual yield. They're saying this reaction produced that much. That's the actual yield. Okay, so this is the actual yield. How do we find the theoretical yield? We do those two long equations, right? So don't be fooled by that. That's the actual yield. Keep doing that. Okay, let's remember that percent yield is the actual yield divided by the theoretical yield times 100%. So they gave us the actual yield. They're also asking us what the theoretical yield is. So we have to calculate that. So we're going to ignore that massive product because that's how much was actually made. That's like when we made the 11 pancakes, but how much in theory could we make? So we have to do these two calculations. 185 grams of Fe2O3. Grams to moles to moles to grams. So we're going to have 3 conversion factors here. Grams of Fe2O3 to moles of Fe2O3 to moles of Fe to grams of Fe. Previous term comes down. This is moles of Fe, and this is moles of Fe2O3. And this over here will be grams of Fe2O3. Does this get a little tedious? Yes, it does. Middle term's the easiest. There's a 2 in front of Fe in the equation, and there's an implied 1 in front of the iron oxide. The last one in this one is easy too. What's the molar mass of iron? We don't have to calculate it, we just look at the periodic table. 55.85. But we do need to calculate the molar mass of the Fe2O3. So Fe2O3, there's 2 irons, so 2 times the 55.85, and 3 oxygens. Came up with 159.7. Anybody else get that? Yeah. Okay. Yesterday I made a lot of mistakes. Grams of Fe2O3 is equal to 1 mole. That's what the molar mass means. And so we stick that in here. 159.7. Let's just go through our units here, grams of that, and moles of that, and moles of this. And we're good. And then we calculate 185 divided by 159.7 times 2 times 58.85. And that would have three significant figures. So 129 grams of iron. And we get to do it again. These problems give you a lot of practice, don't they? Yeah, I'm not so happy about that. 95.3 grams of carbon monoxide. Grams to moles to moles to grams. Grams of CO to moles of CO. To moles of Fe to grams of Fe. Don't go off and calculate something different. These are two different maps that end up at the same destination. Two paths that end at the same place. So it's like Dora's starting from one place and going to the snowy mountains. And Boots is starting from somewhere else and going to the snowy mountains. So don't have Boots end up, at the 7 Seas or something. And reading too much Dora. And now the song's playing in my head too. I won't sing it for you, I'll spare you that. So put these units down here. Moles CO, moles Fe. And always, give it a little once over there and make sure that you're actually canceling them out like you're supposed to. You can't do wishful unit canceling. Some people do that in labs. It's very interesting. Okay, the mole one is the easy one. In front of CO is a 3, and in front of Fe is a 2. So we got that one. The last term is going to be exactly the same as it was above. And then that first term, we need the molar mass of carbon monoxide. I'm going to squeeze that in here, 12.01 plus 16. Which should be 28.01. Is 1 mole. So 28.01 grams per mole. And then we're ready to calculate again. 95.3 divided by 28.01 times 2 divided by 3 times 55.85 equals, and that one rounds to 127 grams of Fe. Wow, those are really close. We haven't seen one so close before. What's the theoretical yield? The smaller one, right? This is the theoretical yield. It's always the smaller one.
That wouldn't be considered a limited product?
There is no limited or limiting product, only a limiting reactant. If you make 2 moles of iron, you have to make 3 moles of CO2. And so the products are always going to come out in a stoichiometric ratio. You can add the wrong amounts of reactants, and one will get used up and one will get left over, but the products are always going to come out okay. So that's the theoretical yield. That's one of the things they ask for. What's the limiting reactant? The CO. So this is our limiting reactant. And then it's asking for the percent yield. Well, let's see if we can squeeze it in up here. The actual yield was 87.4 grams. The theoretical yield is 127 grams times 100%. 87.4 0.4 divided by 127 times 100. And that's 68.8%. 68.8%. Any questions? Yes? The CO is the limiting reactant because that gave the least product, which tells us, as we're reacting the Fe2O3 and the CO, we're reacting them and making more product, we only have enough CO, carbon monoxide, to make 127 grams. And when we run out of a reactant, it stops.
So the theoretical limiting reactant is always the same?
The limiting reactant is always the reactant that gives the theoretical yield. Yep. So you do these two calculations, you pick the smaller number, that's your limiting reactant, your theoretical yield, and then you look back. So here, you're picking the smaller one, and then you trace back and see what gave me that. That reactant is your limiting reactant. Yes, question?
I was just asking for like a test question. Is there a possibility you'll give us a question where we actually have to balance the formula before we do all of this?
No. I will not give you, you could do something like give you the names of two reactants and make you predict the products, balance the equation, write all those formulas, and then do something like this, calculating theoretical yield. I'd give you the actual yield, you have to calculate the percent yield and do the limiting reactant. That would be very, very mean in Chem 20. That's just not, I would never do that to you on an exam. Yeah. It's like, here's one problem. Yeah. Yes?
Round the percentage?
I rounded the percentage to 3 significant figures because both of the numbers that I used to generate that had 3 significant figures. Any other questions? So could there be a question exactly like this on the exam? There could. There could. But a problem like this takes quite a long time. So probably not. Will the components of this be asked in different questions? Definitely. Okay. What's next?